Every natural system uses energy. Energy is one of the handful of unifying themes in all science. Indeed, every natural system has to obey the two laws of thermodynamics. The first law says that energy can change form from one type to another as many times as you want, and the total amount of energy is constant. That's the good news. But there's a downside, and that's the second law, that there are restrictions on how energy can transfer. Heat must flow from hot to cold, spreading out, evening out. There's a built-in direction to the way we use energy. Yet this description of energy fails to capture the depth and the subtlety of energy and its role in our lives. As scientists of the 19th century thought about the implications of energy, they eventually came to a startling realization: the great principle that every isolated system becomes more disordered with time. In this lecture, the 10th of our series, I'm going to introduce the concept of entropy, the tendency of systems to become messier, quite spontaneously, in spite of everything we do. I'll begin by introducing the subtle idea of entropy, which follows logically from other statements of the second law of thermodynamics. The statements, for example, that heat spreads out, or that no system can operate with 100% efficiency. We're going to find out in this context that the second law holds tremendous power and sway over our lives. At the core of the concept of entropy are such human experiences as aging and death, decay. The second law defines the very direction of time. I'm going to end the lecture by examining some of the far-reaching aspects of entropy, including the so-called heat death of the universe and the direction of time. There was a recent commercial for auto insurance on television, and it began with a totally smashed car in the middle of a flower shop, destruction all around. Piles of debris, broken glass, flowers strewn everywhere. Suddenly, the car lurches backwards through the store's plate glass window, which reassembles miraculously. The horribly damaged car rolls up the street, hitting various objects which are put back into position, and gradually pieces of the car attached back on, and at the end of the commercial, the car is in perfect shape in a parking place. That sequence didn't violate the first law of thermodynamics at all, but we know that something's horribly wrong with that picture. We laugh because it defies physical logic. The discussion of the second law of thermodynamics thus far is focused on the behavior of heat energy. And one statement of the second law is that heat flows spontaneously from hot to cold. Another equivalent statement is that you can't build an engine of 100% efficiency that converts heat to work. But as useful as these ideas may be, they miss the real essence of the second law. There are far-reaching consequences of the second law that go beyond just the way heat energy behaves. In its most general form, the second law of thermodynamics comments on the state of order of the entire universe. I'm sure you've noticed the tendency of things in your everyday life to get messier. A new briefcase, you buy a briefcase, you buy a coat or a new car, and it's spotless, it's shiny, it looks beautiful. A year later, you look carefully, and the briefcase has scuff marks on it, the coat's a little bit frayed, the car has dents and dings, and it's going to be dirty. You can clean your home from top to bottom, and a week later, it's messy. It's got dust, things are sort of strewn around. Our bodies, too, they experience this inevitable aging, the decay. It seems like it's an irreversible process. All systems in the universe have this tendency to become more disordered with time. A week ago, I bought my wife a bunch of flowers. And they were brand new, they were beautiful. They're looking pretty sad right now, and the flowers, after a week, they've become something that's only worthy of throwing into the trash. Of course, thanks to the teaching company, these are now a tax deduction, so I guess it's not all bad news. You can devise all sorts of everyday experiments to show this type of behavior, and I just want to share a few of these with you. For example, you've all had the experience of shuffling a deck of cards, and you can order those cards into a perfect array, but as soon as you shuffle them, they become less ordered. And now they're not in as good order. Now, you could keep shuffling these cards over and over and over again 1,000,000 times. They would never become back to the original ordered state. They would never be as ordered as they were when we started. You can take a jar and put colored candies in them, 2 different types, and you can layer those. But if I shake the jar around just a little bit, all of a sudden, they're no longer ordered. Now, I could shake this jar as many times as I wanted to, and they'd keep coming up with new ordered arrangements, but they'd never be as perfectly ordered as they were when I started this. Yet another example. You can take a jar of water and put a drop of food coloring in. To begin with, I had a highly ordered state with perfect food coloring and a clear glass of water. And as things go on, you know what's going to happen. That food coloring is going to spread out, diffuse out throughout the entire jar. These examples are precisely analogous to a situation where a hotter and a colder object come together. The heat energy of the hotter material gradually diffuses into the colder object. In every one of these cases, we could, if we wanted to, reverse the process. I could easily reorder the cards just by spreading them out and putting them in order. I could boil the water and recover that drop of food coloring. I could fix the candies. I could put them back in a layered order if I wanted to. And in theory, if we knew more about human aging, we could reverse that process too. There's no intrinsic reason why humans could not extend lifespan many, many-fold if we knew how to fix the gradual damage, the gradual aging process. All it takes in theory in all of these cases is the use of energy. You take energy, you can reorder a system that has become disordered. The concept of entropy, the disorder of a system, was introduced in 1865 by a German physicist, Rudolf Julius Emanuel Clausius. Clausius was born in Pomerania, which is now a part of Poland, in 1822. He studied at several German universities. He graduated with distinction from the University at Halle. He accepted a professorship at the Imperial School of Artillery and Engineering in Berlin, and subsequently he taught at universities in Zurich and in Würzburg and Bonn, where he died in 1888. Clausius devised the concept of entropy in order to quantify this natural tendency of systems to become more disordered with time. Clausius synthesized the ideas of Carnot and Joule and others, and he published the first clear statement of the 2 laws of thermodynamics in 1850. It was the first time in a publication there was a statement about these 2 laws that we've been talking about that gradually came into being understood over a period of many decades in the 19th century. The second law in this original statement, though, wasn't presented in any rigorous mathematical form. Clausius just noted the tendency of systems to become more disordered with time. He realized that for the second law to be quantitatively useful, it demanded a new, rather abstract physical variable. This variable he called entropy, which is a word derived from the Greek word for transformation. He defined entropy purely in terms of heat and temperature. Entropy, in fact, is the ratio of heat energy over temperature. This definition has very important applications in chemistry and in engineering, where heat is used to do work. But for most of us, and I think this is including most scientists, this definition, heat divided by temperature, is it's a very non-intuitive concept. What Clausius did was to study steam engines. He observed the behavior of steam engines and realized that this ratio of heat divided by temperature must either remain constant or it has to increase. It never decreases. Stated another way, in any heat engine, the heat energy divided by the temperature of the cold reservoir is always greater or equal than the heat energy divided by the temperature of the hot reservoir. Thus, the entropy of a closed system cannot decrease. Entropy can be constant or it can increase. And in most instances, because there's always some natural escape of heat energy into the surroundings, in most cases, entropy increases. Every physical substance has a quantity of entropy, just like it has a quantity of energy. You can measure it, you can give it a unit. Just, at least in principle, you can measure the entropy of a system by measuring its temperature and its total heat energy, although it turns out that that's not so trivial a thing to do. So in this case, you can summarize the two laws of thermodynamics in a very shorthand way as energy is constant, entropy tends to increase. And that's the shortest way of saying the first and second law of thermodynamics. I confess, all this is very abstract stuff. You can express everything I've just told you in mathematical forms with equations, and lots of scientists and lots of engineers have learned to use those equations and do all sorts of different, very important things with heat and energy and so forth. But my impression is that the number of scientists and engineers who really have a deep intuitive understanding of entropy is quite small. This is a really abstract concept, this concept of entropy. So I want to help you with this, maybe a more intuitive way of thinking about entropy. Why should things become more disordered? And you can do this by thinking about natural world at the scale of atoms. Haven't really introduced atoms yet, but all matter, all the things around us are made of atoms. These are tiny particles. They come together to form in chemical bonds, to form the various solid and liquids and gas structures we see around us. And you can think about entropy in terms of the properties, particularly the energy, the kinetic energy of individual atoms. Heat spreads out because some atoms with more kinetic energy collide with atoms that have less kinetic energy, the slower atoms, if you will. And so eventually the kinetic energy of atoms averages out. And this is why heat spreads out. It's just a physical process of vibrating atoms that keep colliding into each other, whether they're in the gas state or a liquid state or in a solid state. Concentrated heat thus spreads out. Ultimately, the order of any system can be measured by the orderly arrangement of these smallest parts, these atoms. Think about some of the materials that you see around you. A crystal of table salt has a highly ordered arrangement of atoms. You have sodium and chlorine atoms alternating sodium, chlorine, sodium, chlorine, sodium, chlorine in a very orderly arrangement. A lump of coal also has a highly ordered arrangement of atoms. It contains a lot of this ordered energy with carbon-carbon bonds and bonds between carbon and hydrogen. Particularly, those are very energetic bonds. You can dissolve the salt in water. You can burn the coal, and you disrupt those bonds. The material becomes more disordered. The entropy increases as you release that heat energy. The arrangement of atoms doesn't have to refer specifically to a solid. You can talk about the arrangement of atoms in a gas as well. And you can imagine gas atoms having different temperatures. They have different velocities. Imagine what happens if you have two reservoirs of gas that are at different temperatures and suddenly you mix them. You dump two bottles of gas, one that's very hot and one that's cold, for example. The separation of the gas into two separate populations is a more ordered state. It's like having all the red marbles in one part of the jar and all the blue marbles in another part of a jar. And as soon as you mix them together, the hot atoms in the hot gas start colliding with the colder atoms, and the temperature averages out because the average velocity of the gas atoms averages out. The entropy, therefore, the disorder of the system increases. This definition of entropy as a measure of the degree of disorder may seem fuzzy, but it was placed on a very firm quantitative footing in the late 19th century by the Austrian physicist Ludwig Boltzmann. Let me tell you about Boltzmann. He was born in Vienna in 1844. He studied at the University of Vienna, where he spent most of his professional life as professor of theoretical physics. He was said to be an imposing man of great physical strength, combined with a kind of sensitivity and humor. He also suffered from severe bouts of depression, and it was during one of these spells that he took his own life in 1906. Boltzmann used what's called probability theory to demonstrate that for any given configuration of atoms, the mathematical value of entropy is related to the number of different possible ways you can achieve a particular configuration. And I'll show you what I mean. Entropy, in fact, is the logarithm of the number of configurations. That's the mathematical form. This is a subtle and a very profound point. let me try to illustrate what Boltzmann meant. I want you to consider, rather than the millions and millions of atoms that form even a tiny part of air, let's just look at 6 balls numbered 1 through 6. 3 of them are yellow, 3 of them are orange. And think about all the different ways to arrange these balls. It turns out that there's 1 times 2 times 3 times 4 times 5 times 6 different arrangements, a total of 720 different ways just to line up 6 balls. And if you go through the math, it turns out in exactly 36 of those ways, you can rearrange the balls so you still have an ordered arrangement of 3 yellow followed by 3 orange. And you can imagine all different ways of moving these around. 36 different ways of doing that. But that's 36 out of 720 different ways. So if I randomly threw down all 6 balls in a row, you'd only have a 1 chance in 20 of having 3 yellow followed by 3 orange. All the other arrangements would be different. A lot of them would have things mixed up where the oranges and yellows are mixed up in various ways, and most of the arrangements would then appear more disordered. And that's a situation with only 6 different balls. Now imagine if I had 1,000,000 balls, or 1,000,000,000,000 balls, or as an atom, trillion atoms. You can imagine there are a few ordered states in which all the hot atoms are in one side of the room and all the cold atoms are in the other side of the room. But the chances, the probability that you achieve such a situation are so infinitesimally small compared to all the disordered arrangements that the disordered arrangements always dominate in the natural world. It's just a matter of probability. So this is the key to understanding entropy. It is a microscopic manifestation of probabilities. It's just like going to Las Vegas, and what are your chances of winning? Well, if you're talking about ordered states in the natural world, your chances of winning are very small indeed. I'm going to shift gears now and look at some of the consequences of the second law of thermodynamics. I'm going to tell you about the so-called heat death of the universe, the nature of time, and also the central biological concept of trophic levels. These are 3 of the consequences of the second law. Arthur Eddington was a very influential 20th century British cosmologist, about whom we're going to learn a lot more in lecture 32. Well, he said, and I quote, "The law that entropy always increases, the second law of thermodynamics, holds, I think, the supreme position among the laws of nature." Well, why did he say this? Why did he think it had such deep and far-reaching consequences? One of the more sobering consequences of the second law is the idea that the heat in the universe must eventually spread out. Life on Earth is possible because the sun provides a steady stream of heat, of radiant energy, to the Earth's surface. The Earth also holds a vast reservoir of internal heat. But if you think about it, in the 1890s, people began to realize that that heat in the Earth is still radiating out into the coldness of space. The sun's energy is radiating out into the coldness of space. Eventually, perhaps billions of years down the road, that heat energy is going to disperse and distribute evenly. The ultimate fate of the universe, therefore, must be for the heat to spread out uniformly, as in the second law. Now, we don't necessarily have to worry about this, especially the discovery of nuclear energy, which provided vast amounts of energy still preserved in the universe today, indicates that it's going to be hundreds of billions of years or more before this heat death really takes place. But nevertheless, it's a sobering consequence to think that the universe itself may end in this kind of whimper-like state with everything at a uniform low temperature, no life possible, nothing of interest ever going on. Indeed, no energy transfer possible because all the energy is taken up in matter at the exact same temperature. You can't do any work if you don't have 2 heat reservoirs at different temperatures. The second law also tells us something about time, the nature of time. Throughout this course, I refer to time in lots of different contexts. I talk about distance equals velocity times time, power equals force divided by time. We experience time as one of the major variables in our lives. We try to deduce historical aspects of things, and time becomes a very important parameter in those kinds of discussions. But what exactly is time? Talk about an intangible physical quantity. What is the nature of this quantity, time? Why does it seem to have a direction from past to future? These are really deep questions, and in many sense these questions are more philosophical. They're beyond modern science. But the second law of thermodynamics gives us some tantalizing insights. Again, I want you to imagine playing your favorite movie backwards. Imagine playing a videotape backwards. Many scenes are going to appear perfectly normal. Drifting clouds on a windy day would look very normal. Blowing leaves, even gently flowing stream, if you couldn't see a very steep slope, would look perfectly natural either way. But some forms of motion would look very, very strange. People diving out of a swimming pool, unbreaking an egg, unshooting an arrow. These are impossible in the real world. You have to ask yourself, why are some actions irreversible? And I think it all ties with this tendency of entropy to increase. The tendency of entropy to increase rather than decrease defines the arrow of time. It defines the direction in which time moves in our everyday experience. When you shake a jar, it becomes more disordered. When you shuffle a deck of cards, it becomes more disordered. When you put food coloring in a jar of water, see? It's spread out quite evenly. That's the direction of time. That's the arrow of time. Glass shatters, milk spills, organisms die and decay. The arrow of time. Of all the great natural laws, the laws of motion, the laws of gravity, the first law of thermodynamics, electricity and magnetism, as we'll see, only the second law of thermodynamics incorporates this arrow of time. Somehow, the second law defines the direction of time. Whether that's a cause or effect, whether we're merely describing some aspect of the natural world that is, it's still a fascinating idea. And that's why scientists who think about energy also think about time. Let's consider yet another example of the second law and its consequences. All living things are subject to the limitations of the laws of thermodynamics. That's pretty obvious. We're living systems, but we're natural systems. We see this in many, many different ways, including the pervasive biological concept of trophic levels. Every organism has to compete for a limited supply of energy. Plants are in this first trophic level because they get their energy directly from the radiant energy of the sun. In the second trophic level, we find herbivores. These are animals that eat plants. But almost 90% of the energy that's contained in plants' chemical substance can't be used. There's an inefficiency here. So, while plants get about 10% of the sun's energy, herbivores only get about 10% of a plant's energy. And then come the carnivores in the third trophic level, and carnivores only get about 10% of the energy contained in the herbivore in the meat that they eat. And so you see this second law of thermodynamics coming in the efficiency of living systems. Plants are 10% efficient, herbivores are 10% efficient, carnivores are 10% efficient. So as you go up the food chain to the largest carnivores, this explains why there are so very few large carnivores compared to the number of herbivores, and then compared to the total biomass of all the different plants. It's a natural consequence of the second law, because you're passing energy through a system, but it's not an efficient passing of energy. It takes 10 herbivores for every carnivore. And if you have a large carnivore that eats other carnivores, those are really going to be rare. This concept of trophic levels, by the way, has real important consequences for the world food management. It takes many times more energy to produce meat and poultry than it does to produce a certain amount of grain with similar nutritional value or the similar number of calories. So for that reason, as the world becomes more and more crowded and more populous, we're going to have to look more and more to plants as our most efficient source of food energy. The second law of thermodynamics, it turns out, is one of the most misunderstood of all natural laws. The law is often invoked by creationists to prove that life could not possibly have evolved on Earth. And let me tell you about their rationale. It goes something like this. They say living things are exceptionally ordered states. Every single cell in our bodies, and we have 100 trillion cells in our body, every cell has countless trillions of atoms that are precisely and intricately ordered. Certain atoms, if you just move certain atoms out of position, the cell doesn't work anymore. If those cells don't work anymore, the body doesn't work anymore. So life is probably the most ordered system we can imagine. The human brain is probably the most ordered and intricate object we can conceive of. Well, given the second law, it seems, since systems tend to become more disordered with time, it's inconceivable that such an ordered system could have evolved within the context of the second law, because systems tend to become more disordered, not ordered like the human brain. So how could you evolve life? For this reason, creationists say you have to have a miraculous creation of life. You can't imagine a natural system evolving life in this way. This argument, though, misses an important aspect of the second law. You can have locally ordered states that arise, and they arise around us all the time. Think about a pan of salt water put out in the sun. The sun evaporates the water, and salt crystals, incredibly ordered salt crystals, form where before there was a very disordered arrangement of sodium and chlorine ions in the water. The key is that the sun adds energy to the system locally. But if you think of the entire system, including the sun and the earth, the sun is becoming more disordered. It's burning up its fuel. And as it burns up its fuel, the total system becoming more disordered. But locally, you can have pockets of increasing order. Every time a plant grows, every time you get a cut and it heals, in that sense, you're sort of overcoming the second law because you're taking energy and you're fixing damage. You're making things better when before they were worse. So we see every spring as new plants arise all around us, we're seeing these so-called violations of the second law, but they're not violations at all. It's just a reshuffling of energy. It's systems that have learned how to use energy and collect energy from their surroundings. The surroundings have entropy that's increasing, but the individual objects then become more ordered. And that's how you can explain the origin of life. It's just another example of this very common natural process that occurs around us, albeit a remarkable one. Let's not get away from that. You might think that energy is by now so well studied that we know it all. We know pretty much everything there is to know about energy. But I think that may not be so. There's one nagging aspect of energy that I believe science has not yet fully addressed. I may be in a minority on this, but think about it. There's a tendency of physical systems to spontaneously become complex locally, as I just said, even though they become globally disordered. What do I mean by that? Well, there's a seemingly universal tendency for systems with large number of components to display complex behavior that you wouldn't normally see in the individual components. And you can see so many examples. Individual sand grains can just lie there, but if you put enough sand grains together, you get dunes, you get ripple marks, you get all sorts of complex behavior that you'd never predict from a single sand grain. Atoms form planets, and then life forms from those planets. And then consciousness forms from life, and you have these emergent, complex processes that seem to arise spontaneously out of local order in an otherwise large system in which the entropy is increasing. In each of these cases, you see local states of extremely high order arising from a large collection of small particles, whether they be cells or atoms or so forth. These are what we call emergent properties. Complexity seems to just arise in the universe, and as yet there's no law of thermodynamics that describes how complexity can arise. It doesn't fit into the first law, it doesn't fit into the second law. Perhaps there's a third law. Part of the answer may lie in deep connections between the concept of entropy and the concept of information. But we're really a long way from a full understanding of this point. In any case, I'm willing to bet personally that someday, perhaps soon, there's going to be a third law of thermodynamics. That's one of the exciting things about science. We keep coming up with new ideas. Science is an endless frontier. Let me summarize this lecture on the second law of thermodynamics. This law provides a framework for understanding so many of the directional events in our lives. The simplest statement of the second law is that heat tends to spread out evenly. And that's a special case of this more general tendency of systems to become disordered, a tendency that is quantified by the concept of entropy. Entropy can be defined formally as the ratio of heat energy divided by temperature, or it can be treated statistically as a measure of the number of possible configurations of a system, that is, the probability of having an ordered versus a disordered state. In either case, the entropy of a closed system will not decrease spontaneously. And then by defining the sequence of possible events, the second law of thermodynamics provides a definition of the arrow of time. Energy is going to return over and over and over again in these lectures as an underlying theme. But first we have to take a closer look at two of the forces that play a vital role in our everyday life. That's electricity and magnetism, and that's the subject of the next lecture.